The Thomson lamp paradox describes a scenario in which a lamp is toggled on and off infinitely many times within a finite time interval. Specifically, the lamp is toggled at times given by a specific sequence. This paper introduces and evaluates the series framework given by the series work at K, and tail at K, abbreviated by the initials WWT, as a resolution to the paradox, addressing the state of the lamp at time t equals 1, proving relevant theorems, and analyzing, and responding to skepticism. The work is defined as the limit of work at K as K approaches infinity. Tail at K is defined as the difference between work and work at K. Theorem 1 states that work at K equals a specific series sum, and the sign of work equals S sub 0. The proof involves the lamp state between toggles and the convergence of the series. Verification examples confirm the theorem for different initial states S sub 0. Verification examples show that for S sub 0 equals +1, work at K equals 1 and work at K equals 2 calculations verify the theorem, and similarly for S sub 0 equals -1. The theorem concerning tail at K is also verified through similar calculations. The proof shows that the sign of work determines the initial state S sub 0, and the resolution of the paradox naturally follows from this, indicating that the lamp's final state must be the initial state S sub 0. This conclusion is supported by the convergence of the geometric series used. What is happening is that the WWT framework resolves the Thomson lamp paradox by shifting attention from the oscillating toggle sequence to the convergent quantity work at K. Unlike the state sequence itself, which alternates indefinitely, +1, -1, +1, and does not approach any limit, the series defining work at K incorporates diminishing geometric intervals, ensuring smooth convergence. Thus, work at K steadily and unambiguously approaches its final limit, providing a stable, definitive endpoint to the paradox. Yet, the associated quantity tail at K, the residual of the total work relative to any finite stage, does oscillate as it approaches 0. While work at K moves consistently toward the final value, tail at K fluctuates between positive and negative values, capturing the paradox's inherent indeterminacy within its limiting behavior. This oscillation in the tail term vividly illustrates why observers of the paradox might perceive persistent uncertainty, even though the overall structure dictates a definitive outcome. The WWT framework thus resolves the paradox by explicitly distinguishing between the well-behaved, converging quantity, work at K, and the inherently oscillatory tail at K. This dual perspective preserves the paradox's philosophical richness, underscoring how infinite processes, carefully handled mathematically, can yield definite answers. The conceptual strength of WWT is precisely this clarity. It acknowledges infinite oscillation at the microscopic level, tail, K, yet confidently delivers a resolved and stable macroscopic conclusion through work, K. The sequence itself, +1, -1, +1, -1, does not converge in the usual sense. However, the carefully structured timing and the geometrically decreasing intervals, 1/2, 1/4, 1/8, create a context that results in a convergent series, work at K. The limit isn't taken from the toggling states alone but from the weighted sum, work at K, which includes the time intervals explicitly. This isn't a flaw. Rather, it's precisely the innovation and strength of the WWT framework. It explicitly leverages the geometry of the intervals to produce convergence and resolution. It effectively bridges the gap between the non-converging behavior of the toggle sequence and the convergent mathematical structure it generates. In other words, The final state at equals 1 being sub-zero is not arbitrary. It emerges naturally because the mathematical structure, geometric intervals and alternating states, inherently dictates how the limit behaves. The deterministic outcome isn't forced onto the paradox externally. Instead, it's derived directly from the structure of the toggling scenario itself. If the concern is philosophical, as many are with this paradox, the framework essentially argues that the apparent indeterminacy of the paradox arises from looking solely at the toggle states without incorporating the critical temporal weighting. Once the intervals, time factors, are included, the limit naturally reflects the original structural logic, resulting in determinacy.